Hello and welcome to the Modern Embedded Systems Programming course. My name is Miro Samek, and in this 8th lesson on state machines, I would like to drill deeper into the semantics of hierarchical state machines. Specifically, in this lesson, you will examine a hierarchical state machine with multiple levels of state nesting. You will then see how this more advanced state machine handles various transitions and exactly which actions are executed in which order. To remind you quickly what happened so far, in lesson 40 you designed a relatively simple hierarchical state machine for your time bomb application, which you first coded manually, and then, in the last lesson 41, you generated the code automatically. However, the time bomb state machine had only one level of state nesting and didn't really demonstrate the richness of semantics enabled by state hierarchy and transitions between states nested at various levels. So today, to explore what's possible and to learn how exactly a more advanced hierarchical state machine can handle various transition types, I'd like you to run an example already provided in the QPC framework. Specifically, in the last lesson 41, you've seen how to download and install the QP bundle software, which among others contains the QN modeling tool, QP frameworks, as well as many other supporting tools, some of which you will have a chance to use today. So first, I'd like you to go to the QPC examples workstation directory, because today you will see an example that runs on your workstation as opposed to an embedded target. I will show you how to adapt this example for your Tiva-C Launchpad embedded board in one of the future lessons. But for today, choose the QHsmTst example and find the QM model file, which I'd like you to open in the QM modeling tool. Once the model opens, expand the HSM's package and double-click on the QHsMTST class to show the associated state machine. Before anything else, let's start with locking the model, which will protect it from any accidental edits. So this hierarchical state machine is taken from Chapter 2 of my book Practical UML Statecharts in C and C++, 2nd edition, which is available in PDF from the statemachine.com website. This example is obviously contrived in that it does not model any real system, but it has been carefully designed to contain all possible transition topologies up to 4 levels of state nesting. This includes regular transitions between various levels of state hierarchy, as well as internal transitions. The state machine contains 6 nested states: S, S1, and S11 on the left, and S2, S21, and S211 on the right. The various transitions are triggered by events named A, B, C, and so on through I. These events correspond to the ordering of transition types from the simplest to progressively more complex in the state machine algorithm used inside the QP framework. Also, all transitions as well as states have actions. These actions produce information as to what exactly happened. For instance, entry action to state S2 produces output S2 entry, while the exit action produces output S2 exit. Similarly, the action on state transition A in state S1 produces the output S1A, while state transition A in S21 produces the output S21A. By the way, this kind of output with the information about the code execution is more technically called software tracing, because the output generated by the instrumentation added to the software allows you to trace the code execution. Such information can be very useful for debugging, testing, and fine-tuning your code. Software tracing is a very important concept, and I will talk about it in the future lessons of this video course. But going back to your state machine, it also demonstrates guard conditions, and for that it has an attribute foo, which is used inside guards and also modified in some transitions. So now let's generate the code from this hierarchical state machine, exactly as you did in the last lesson 41. By now, the generated C code should be familiar to you, because this is the same optimal state machine implementation that you've been using since lesson 39. In principle, you could write such code manually, because in fact it was originally designed for manual coding. But here I have a personal story which convinced me to automatic code generation. So, as I already mentioned, I designed the QHsmTst example for the practical UML Statecharts book. At that time, the QM tool didn't yet exist, so of course I coded it manually and drew the diagram in Visio. After QM was developed, I wanted to provide all examples from the book as QM models. Interestingly, the QM-generated code from the QHsmTst state diagram produced a different trace than my manually written code. My first suspicion was the QM code generator, because the tool was new back then. But to my surprise, the generated code turned out to be right, and the problem was with the diagram. Specifically, the transition G in state S21 went all the way to state S11, whereas it should go only to the S1 superstate. This is indeed what the current QHsmTst model shows. This was a big lesson for me, and I hope it will inspire you as well. Since then, I just don't leave things to chance anymore and always generate code automatically. But I digress, because now you need to build the generated code. For that, open a command prompt and change the directory to your QHsmTst example. This directory contains a Makefile, which should work on Windows as well as Linux and Mac OS. This Makefile is designed to be easily customizable for your own applications, whereas you typically don't need to change anything beyond that line. To execute a Makefile, you need the Make utility. But if you've installed QPBundle as shown in the last lesson 41, Make should be directly available in your path. Also, the Makefile assumes that the GCC GNU CC++ compiler is directly available in your path as well. Again, if you've installed the QPBundle, you should have the GCC compiler available. So now just type make to build the code. This produces the executable in the build directory. To run this executable from your command prompt, type build /QHsmTst. This produces some printouts from your software tracing instrumentation in the state machine actions. By correlating this tracing information to the state diagram, you will be able to see exactly what the state machine is doing and in which order. Please try to pay attention to the details here, because they are important to learn and understand the semantics of hierarchical state machines. So starting with the topmost initial transition, the first action, top init, is the one attached to the transition itself. Please note that besides producing the output, the action also initializes the member foo to 0. This will be important later for evaluation of guard conditions. Please also note that an initial transition is allowed to cut through more than one level of state nesting, like here it cuts through state S, and goes directly to state S2. However, every state crossed by a transition, initial or regular, must be still properly entered, and therefore the next action executed is the entry action to state S, followed by entry action to state S2. Now, the topmost initial transition ends on state S2, which is called the explicit target of the transition, but the trace does not stop there. This is because the semantics prescribes that any transition, including initial transition, needs to drill into the substates as long as there are initial transitions nested directly in the target state. And indeed, there is an initial transition nested directly in S2, so it is taken. Next, S21 is entered and S211 is also entered. S211 is called a leaf state because it has no further substates or nested initial transitions. Therefore, the run to completion step completes here and the hierarchical state machine is said to have reached a stable state configuration. The last entered state becomes the current state. At this point, you can start dispatching events to your state machine. You do this by typing on your keyboard. For example, letter G dispatches the corresponding event G to the state machine. Per the semantics of hierarchical state machines, the event G is handled in the following way. First, the current state, S211, attempts to handle the event. However, state S211 does not have any transitions labeled with G. So the event is passed on to the next, higher level state in the hierarchy, which is the state S21. S21 has a transition triggered by G, so it executes the action associated with the transition and produces the printout, S21G. Next, the state machine executes the transition chain that exits the source state configuration and enters the target state configuration. The transition chain starts with exit actions from all states up the state hierarchy to the so-called least common ancestor, LCA, but not exiting the LCA itself. The LCA of S21 S1 pair of states is their common superstate S, so all states up to S, but without S itself, are exited. Next, the target state configuration is entered in the exact opposite order, that is, starting from highest levels of state hierarchy down to the lowest. The transition G from state S to 1 terminates on state S1. However, S1 has a nested initial transition, so it is executed and S11 is entered. This is a leave state, so the RTC step completes. Next, let's dispatch the event I. Again, the current state S11 does not have any transitions labeled I, so the event is passed on to the next level of state hierarchy, that is to state S1. S1 has an internal transition triggered by I, therefore S1 handles the event and produces the printout S1I. And at this point the processing ends. No change of state ever occurs in the internal transition, even if such transition is inherited from higher levels of state hierarchy. The current state remains the state S11. Next, let's dispatch event A. As before, the current state S11 does not prescribe how to handle A, so the event is passed on to the superstate S1. S1 has a self-transition triggered by A, so it executes actions associated with that transition, producing the printout S1A. This time, however, A is a regular transition, which requires exiting the source state configuration and entering the target state configuration. The LCA of state pair S1, S1 is S. So all states from the current state up to S, but excluding S, are exited. Next, state S1 is cleanly re-entered by executing the entry action to S1, initial transition in S1, and entering the S11 leave state. At this point, I'd like to make two observations. The first is that in hierarchical state machines, self-transitions like S1A here are different from internal transitions like S1I here. This is not necessarily the case in the classical, non-hierarchical state machines without entry and exit actions to states, where self-transitions are used exactly to cause a reaction in a given state. And the second observation is that in hierarchical state machines, a self-transition is an idiom to cleanly reset a given state context by cleanly exiting and re-entering a given state. Such self-transitions can be useful for various cancel operations, like the cancel button in a calculator. Now let's show the current state, which is still S11, and dispatch event D. S11 has a transition D, but this transition has a guard, me foo. Foo is an attribute of the state machine which was initialized to 0 in the topmost initial transition. Therefore, the guard condition me foo evaluates to false. According to the UML semantics, this is treated as though transition D was absent in S11, and therefore the event D is passed on to the next higher level, that is to state S1. State S1 also has transition D, but with the complementary guard, not me foo. This time the guard evaluates to true and the transition is taken, producing the S1D trace. Please note that the action on that transition also changes the value of the attribute foo to 1. After this, all the appropriate exit actions up to the LCA, which is state S, are taken, followed by entry actions back to S11. The current state becomes again S11. Now, when you dispatch another event D, the guard me foo in transition S11D evaluates to true, and so this transition is taken. This time the LCA is only S1, so fewer exit and entry actions are executed. Event C dispatched to the state machine demonstrates again that all exit and entry actions are always executed, regardless of which transitions are in between. For example, the nested initial transition in the explicit target state S2 goes to substate S211, cutting through the substate S21. However, still, the entry actions don't skip the entry to S21 before entering the S211 leave state. This example demonstrates once again the powerful concept of guaranteed cleanup of the source state configuration through the exit actions and guaranteed initialization of the target state configuration through the entry actions, regardless of the complexity of the exited entry path. Interestingly, in hierarchical state machines, the exact same transition can cause different sequences of exit actions depending on which state inherits the transition. For example, let's now dispatch event E twice in a row. Each time the event triggers the same transition as E, but the actions executed are different, because transition E fires from different state configurations, once when the current state is S211, and next when the current state is S11. For example, let's now dispatch event G to change the current state to S211. And after this, two events I in a row. The first I triggers transition S2I because the guard not me foo is true. Please note that the action on this transition also sets foo to 1. The next event I does not trigger S2I because this time the guard not me foo evaluates to false, and so the event is passed up to the superstate S. The internal transition SI has a complementary guard, which is true, so the transition SI is taken. Of course, in case of internal transitions, there is no change of state, so no exit or entry actions are ever executed. Now let's terminate the QHsMTst executable by pressing the escape key. But you can learn much more by running this example yourself, dispatching various events to it, and studying the software trace it produces. Now, if you wish to play with the example and modify it, you can certainly unlock the model and change things directly in the QPC folder. But perhaps a better idea is to make a local copy of the example and make any changes there. So let's just do that as a coding exercise for today. In the File Explorer, copy the QHsMTst example directory and paste it into your projects for this video course. Next, rename the QHsMTst directory to Lesson 42. Get inside the Lesson 42 directory and double-click on the model file to open it in QM. Now copy the full path to the new directory, and in your command prompt, change directory there. The directory contains the copied Makefile that you already used in the original location, so let's try it again by typing make. The build fails because the qpc.h header file cannot be found. When you open the Makefile, you can see that this is because the location of the QPC framework has been defined as a relative path. This was appropriate for the original QPC examples because it allows you to install QPC anywhere in your file system and still have all the Makefiles work. But it doesn't work anymore in a folder that is outside the QPC directory tree. You have a few options to fix the issue. First, you can define the QPC environment variable, which the Makefile will then take instead of using the relative path. You can do it permanently from Settings, System, About tab, and Advanced System Settings link. Here you click the Environment Variables button, where you finally can add your new QPC variable. Alternatively, you can set the QPC variable locally at the command prompt. For the sake of this exercise, let's do it locally. Now the build succeeds and you can run the build QHsMTst executable as before. Your other option is to change the QPC variable in the Makefile itself, which will then work without you remembering to set QPC the next time. Alright, so now let's get back to your local QHsMTst model and take a look at the few issues that came up during the explanation of the hierarchical state machine semantics. First, I'd like to explore a little deeper guard conditions, and specifically the propagation of events to the higher level states when a guard evaluates to false. For example, this happens when you get to state S11 and dispatch event D. The guard condition on transition S11D evaluates to false, and the event is propagated to the higher level state S1. This might be what you want, but sometimes you might exactly not want to propagate the event, even when the guard evaluates to false. You can model this by attaching a special, explicit complementary guard, else, like this. Now you need to regenerate the code and rebuild the program. When you run it again, get to state S11 as before and dispatch event D. As you can see, this time D produces no output because the event is ignored due to the guard, but the event is no longer propagated up to state S1. By the way, the special else guard and more tips for working with choice segments are described in the QM online manual. Another aspect of a QHsMTst state machine that you can change is how it exits. Specifically, as you can see in the software trace, the execution stops abruptly without any cleanup, that is, without executing the appropriate exit actions from states. This happens because the terminate event, dispatched when you press the escape key, is an internal transition that, as you've learned today, never triggers exit or entry. To execute the exit actions, you need to turn terminate into a regular transition, that is, it needs to go to a state, which you can call final. Now you can move the BSP exit action from the terminate transition to the entry action to final. This will exit the application, but only after the whole chain of exit actions from the sSuperstate has been executed. As usual, you need to regenerate the code and rebuild the executable. When you run it and press escape, you can see that now it performs cleanup. Interestingly, when you run it again, but change state before pressing escape, the cleanup is different, because it is specific to the current state when the application is terminated. This concludes this lesson about the semantics of hierarchical state machines. I hope that you have now a better idea how HSMs work, and you gain some appreciation for the richness of semantics that state hierarchy offers. Of course, you might still have questions as to how exactly certain transition types will be handled. But here, the QHsMTst example can help, because it has been specifically designed to contain all possible state transition configurations up to 4 levels of state nesting. This allows you to quote-unquote answer all your questions by running the example and dispatching the events to trigger the specific transitions. If you like this channel, please give this video a like and subscribe to stay tuned. You can also visit statemachine.com/video course for the class notes and project file downloads. Finally, all the projects are also available on GitHub in the Quantum Leaps repository Modern Embedded Programming course. Thanks for watching.